The universe's speed limit is changing, and nobody can stop it. The lab clock wasn't wrong. It was disagreeing. A laser beat that had lined up for months slid by a few parts in 1018, like a metronome nudging off the bar. "Check the air," someone muttered. The grad student hovered over the log window, finger stiff above enter, because last year's value didn't match tonight's. Then a message from across the ocean. A second lab saw the same lean. Different atoms, different noise, same direction, and the whispers went further back, way back, to light that left the first quasars. If the universe's speed limit is moving, everything you thought was nailed down starts to wobble. The first crack, Webb's ancient quasar whispers. To understand why a tiny wobble could matter, we need to go to the oldest readable pages in the universe's library. Quasars, monsters powered by black holes in the early universe, shine so brightly that their light threads through intervening clouds of gas. Those clouds carve fingerprints into the spectrum, razor-thin absorption lines from atoms and ions. Each line lands at a frequency set by the fine structure constant, alpha, which stitches together electromagnetism's strength, the electron's behavior, and the speed of light. Change alpha by a whisper, and those lines shift by measurable, patterned amounts. The James Webb Space Telescope pushed that search deeper. Its near-infrared spectrographs reach redshift Z approximately 6.575 epochs when the universe was under about 800 million years old. In that era, metal-poor gas imprinted fine structure splittings that today sit in Webb's sweet spot. Teams targeted known high-Z quasars, chasing doublets and multiplets whose separations are especially sensitive to alpha. The stakes were simple and huge. If those separations don't match laboratory values, either our instruments lie, or the universe's rules aren't identical everywhere and everyone. Here's what actually happened. You stack hours of exposure. You calibrate with lamp lines and eidolons. You correct drifts with laser frequency combs when you can, or with cross-calibrations to ultra-stable spectrographs on the ground. Then you fit velocity components, sometimes dozens, because intergalactic gas isn't one neat cloud but a tangle of clumps. In the best systems, the pattern across different ions locks in the redshift. What's left to move are the splittings that track alpha. And in a handful of pristine high redshift absorbers, those splittings leaned. Not wildly, not unanimously, but they leaned the same way. Meanwhile, something else was happening in the archives. Keck and VLT spectra, older, noisier by today's standards, got a second life through new pipelines. The big villain in the last round of alpha wars was wavelength calibration, long-range distortions that bend the ruler you're measuring with. By anchoring UVES data to HARPS and using comb-calibrated segments where available, researchers carved down those distortions. Noise shrank. Systematics that once swamped sub-ppm signals got caged. Some supposed variations evaporated, but a subset didn't. Weighted carefully, they whispered the same lean as the new Webb data. The human part matters. A principal investigator stared at a draft figure for weeks, the bars barely peaking past zero. She kept asking the same question in different clothes. Is this our instrument learning to breathe or the cosmos? She had a postdoc rerun the line decomposition with alternate priors. She asked a rival to try a blind refit. She even pulled a system out of the sample because a telluric residual could mimic a shift. It hurt. It made the plot cleaner. The lean stayed. What nobody knew at the time was how much the sky's geometry would start to matter. When you project measured deltas on a map, any pattern risks being a selection effect. Observations favor where telescopes point and which quasars are bright enough. But when the Webb points overlap with older Keck and VLT sightlines, an odd thing appeared. Not a patchy mess, but a faint suggestion of a gradient. A dipole-like tilt in the measurement signs, hovering just above the noise. It wasn't a discovery. It was a nudge that said, look again. This was the moment everything changed for the people doing the work. They realized the question wasn't only whether alpha varied, but whether it varied with a direction and a time. That meant tracking when, not just where. For high-Z systems, time is baked in by distance. For the lab, time is on the wall. If both hinted the same way, the story would get uncomfortable fast. In the aftermath of early web runs, teams submitted cautious abstracts. No claims of discovery, no triumphant constants rewritten. Instead, a convergence of small, independent results that refuse to cancel. Consistent with a minuscule drift is not a line that lights up headlines, but it's the kind of line that keeps people up at night. Meanwhile, across town, in metrology labs with vacuum chambers, optical cavities, and atoms pinned in lattices, another kind of whisper started to sync up with the ancient ones. Clock ratios, immune to many shared errors, began to slide by the same barely their amount. The sky was hinting, the labs were listening, and between them a pattern was starting to form. Clocks that accuse, atomic time versus the universe. While the sky was whispering through ancient light, labs were hearing it in the present tense. Atomic time underwrites modern life, GPS triangulates, power grids stay in phase, finance ticks trades into order, secure communications share a rhythm. All of that rests on the quiet arrogance that certain transitions in atoms don't move. The claim is simple: count the same thing, get the same second. But what happens when different atoms begin to disagree in lockstep? Get this: optical lattice clocks made from strontium and ytterbium, single-ion clocks based on aluminum and mercury. They're not just precise, they're comparable. You don't trust one clock. You trust ratios between clocks because ratios cancel the shared noise, temperature, vibrations, laser wander. National labs run these comparisons across continents with fiber links and satellites, stitching a network that can see changes smaller than a part in 1018, uncertainties so low they wouldn't gain or lose a second in roughly 15 billion years. Those ratios are where the discomfort started. It wasn't a single eureka. It was a spreadsheet that wouldn't stop leaning. IB/SR ran a hair high in Boulder. In Tokyo, Al+/IB slid the same direction. In Paris, a SR/SR comparison, two identical clocks looked boring, but SR/IB echoed the drift. Cross-lab, cross-species, the sign kept matching. At first, everyone blamed the usual suspects. Blackbody radiation shifts. Did the temperature model miss a tenth of a Kelvin? Vibration pickup. Did a new air conditioner sync with the interrogation cycle? Lattice light shifts. Was someone detuned by a megahertz without noticing? A metrologist woke at 3 a.m. to rerun the Allen deviation plots. He stared at the slope, white frequency noise rolling into a flicker floor that shouldn't have been there if it was just environmental. He emailed at 3:17, recomputed drift with last month's thermal corrections. Sign unchanged. Nobody cheered. They made coffee. Then the human part cracked open. A transportable lattice clock missed lock during a public demo, minutes before a transatlantic comparison slot. Two seniors wanted to pull the plug. A junior refused, swapped a cavity heater set by 20 mK, and relocked with seconds to spare. The ratio stream came back up and kept the same tiny slope it had before the scare. The room stopped blaming gremlins and started blaming the universe. Meanwhile, something else was happening in the way these labs talk. International time is built from hundreds of clocks, weighted and averaged into a standard that everyone steers toward. The people who maintain that standard keep lists of caveats that almost nobody reads. Suddenly, those caveats mattered. If alpha, or the electron-to-proton mass ratio mu, were nudging, different clocks would move differently, because each atomic transition depends on alpha and mu in its own way. That's the trick. You don't need to know alpha. You read the fingerprint of its change in the pattern of drifts. So they attacked the systematics. They measured blackbody environments with radiometers, tightened cryoshields, recalibrated trap voltages, and cross-checked with transportable clocks parked in the same room as their rivals. A lab in Germany flew a comb-calibrated portable to Italy, linked it by fiber to France, and watched the ratio evolve over weeks. Temperature cycles were modeled out, vibration canceled by active isolation. The residuals were still there, faint and stubborn, forming a slope that wouldn't average to zero. Here's where it gets uncomfortable. In Boulder, the IB/SR ratio plotted against the day of year showed a tiny wobble, an annual term on top of a trend. In Tokyo, AL+/IB hinted at the same phase, shifted by the offset you'd expect from local corrections. They didn't know if it was Earth's orbit changing the gravitational potential or a seasonal artifact sneaking through the thermal model. They did what careful people do, extended the datasets, blinded parts of the analysis, and asked others to find the wobble without knowing which line was which. The wobble weakened in some sets, persisted in others. The trend remained. A micro-story unfolded in a cleanroom half a world away. A technician, normally invisible to papers, taped a note above a rack. Trust ratios, not absolutes. He'd seen a firmware patch quietly fix a laser glitch that had lived there for years, and he didn't trust any single number anymore. Ratios let him sleep. Networked metrology turned a local curiosity into a shared problem. Labs reported not just numbers but full uncertainties. Contributions from lattice shifts, Zeeman effects, probe-induced shifts, collisional shifts, servo errors. Committees that once debated commas debated whether to flag a possible common mode cosmological term without laughing. You could feel the room clutching at conservatism and letting go, finger by finger. The stakes were bigger than physics pride. If clock ratios drift at 1018 per year, GPS satellites, which already correct for relativity, will need DriftAware models baked into their timekeeping. High-frequency trading firms, quietly some of the fiercest time users on Earth, started asking for briefings. Power grid operators who live by phase started patching their phasor measurement units with software that could ingest corrections if the standards bodies ever endorsed them. Everyone wanted to be ready while pretending nothing was happening. Meanwhile, across town in a different building, a theorist sketched how a rolling scalar field coupled to electromagnetism would tug different clock species by different amounts. The lab folks ignored the jargon but appreciated the table. SRVs IB/Vs AL plus versus HG plus. If the field was real, the pattern would pick it out. This was the moment everything changed in timekeeping. The idea that the second was a number you realized gave way to a second you tracked. The universe, if it was breathing through alpha and mu, was audibly exhaling in the most precise machines we've ever built. And if geology had anything to say about it, the whispers wouldn't stop in cleanrooms. They'd echo from 2 billion years underground. Fossil physics, Oklo's 2 billion-year reactor. While the clocks argued with the present, the ground kept a ledger from deep time. In Gabon, West Africa, miners once cut into a uranium seam and found something that shouldn't exist. The ore was missing a fraction of the fissile isotope U-235, as if someone had run a reactor there and burned fuel. They had, just not someone. About 2 billion years ago, groundwater moderated neutrons in a rich uranium deposit, and nature built a fission reactor that switched on and off for roughly 100,000 years as groundwater ebbed and flowed. That fossil reactor, Oklo, is a time capsule for fundamental constants. Here's why the stakes are real. Nuclear reactions aren't just about raw chance. They sit on razor-thin energy balances. In Samarium-149, a notorious neutron poison inside reactors, there's a resonance, an energy where it gobbles neutrons with ferocious appetite. That resonance energy depends on the strong force, electromagnetism, and the masses of particles tied up by quantum glue. If alpha or the nuclear parameters were different when Oklo ran, the samarium resonance would shift, changing how much samarium got consumed and how much neodymium and other daughters piled up. Measure those leftovers carefully, and you're reading the settings of physics from 2 billion years ago. Action first. Geochemists drill cores, isolate rare earth elements, and use mass spectrometers to count isotopes with absurd precision. They reconstruct the burn history: how hot, how long, how often the reactor cycled as groundwater breathed through porous rock. Then nuclear theorists take the baton, turning isotopic ratios into constraints on resonance energies. The math isn't friendly. You need reactor models, neutron spectra, and cross-sections that change with temperature. But when the dust settles, you can say, if alpha had moved by more than a few parts in 10·7 over 2 billion years, Oklo would look different than it does. The impact is subtle, not cinematic, but it's heavy. Those analyses squeeze the room for drifting constants to a sliver. The room isn't zero. When models include realistic geochemistry and reactor conditions, the limits relax a hair. That hair matters. The best bounds still allow a minuscule drift, small enough to be invisible to almost everything, large enough to rhyme with what clocks and quasars were hinting. Then a twist, quiet, technical, and contentious. Updated neutron capture models, with better treatments of nuclear-level densities and temperature effects, widened that sliver just enough to reopen debate. If the samarium resonance energy shifts by a tiny amount with environment, or if the thermal spectrum in Oklo's water-moderated core was a bit softer than assumed, you can absorb some of the previously forbidden drift. It doesn't license wild change. It acknowledges that the fossil record, like any archive, has smudged ink in places. A human moment anchored the argument. At a conference where bold claims get applause and careful caveats don't, a geochemist presented boring anomalies, fractional permal deviations in neodymium isotopes that didn't fit the tidy model. Hands shot up. Someone suggested contamination. Someone else blamed metamorphism. She stood there steady and said, "We cleaned the samples 6 different ways. The effect survives only in reactor zones. If it's boring, it's also real." The room went quiet in that way people do, when they suspect the work is right but inconvenient. Meanwhile, something else was happening in the cross-checks. Independent groups revisited gadolinium and ruthenium signatures, not just samarium, to avoid leaning on a single nuclear pivot. The triangulation improved. No single isotope carried the burden of proof. The portfolio pointed to the same conclusion: tight bounds, not a straitjacket. Compatible with a drift at or below the levels tickling modern clocks and teased by distant light. This was the moment everything changed for the timeline. We had 3 baselines: ancient Earth, Oklo's ledger constraining average behavior across 2 billion years; ancient light, quasars giving snapshots in the early universe; modern labs, clocks reporting in the now. If a model could thread all 3, respect Oklo's narrow corridor, match the sky's faint gradient, and fit the lab's ratios, it wouldn't just be plausible. It would be dangerous, because it would demand that our constants are values of fields that move. In the aftermath, the Oklo file stopped being a cudgel to beat down drift and became a calibration point. A wall, yes, but a wall with a doorway cut into it. The question changed from did constants vary, to how much, how fast, and along which direction in parameter space. And with that reframing, attention shifted to the map the 3 baselines seemed to sketch, a pattern emerging that, if real, would pull at the symmetry we thought the cosmos lived by. The pattern emerges, a direction in the drift. While the data piled up, a question kept tugging at the edges. Were these tiny leans random specks, or were they pointing somewhere? The cosmological principle says there isn't a somewhere. On large scales, no preferred spot, no special direction. But when the quasar deltas and the lab ratios were plotted not just against time, but on a sphere and a calendar, a faint arrow started to show. Start with the sky. Those high redshift absorbers weren't evenly spread. Telescope time lives where the weather and the instruments do. Even so, when you assign each sightline a sign, alpha a little bigger here, a little smaller there, and you weight by sensitivity, the map doesn't look like static. It looks like a tilt. Measurements on one side of the sky slightly favor one sign, the opposite hemisphere the other. A dipole, fragile, teetering on significance. But it survived reasonable ways of slicing the data. Meanwhile, the labs had their own map, not across space but across months. Ratios didn't just drift, some of them seemed to breathe with the year. If a scalar field coupled to gravity or ambient density, you'd expect Earth's elliptical orbit to modulate the effect as our gravitational potential changes. The phase would be predictable. In Boulder, Paris, Tokyo, the tiny seasonal terms where they existed, lined up within uncertainties, a wobble on a slope. Seasonal artifacts can fake that, sure. But the phase shouldn't land right by accident across different setups. This was the moment everything changed in how people framed the hypothesis. It wasn't just alpha might vary. It was alpha might have a gradient and we might be moving through it. A direction in the drift means the universe is a little less even than the textbooks promise. That teases at symmetry, rotational invariance on cosmic scales, the thing that makes the sky statistically uniform. Break that even slightly and you're chipping at the foundation. The action got serious around a whiteboard filled with vectors. One team took the quasar catalog, purged systems with any whiff of calibration ambiguity, and fit a dipole plus monopole model, a constant offset plus a directional gradient. They let the data choose the axis. The vector landed not far from some infamous CMB oddities, alignments of the Lowenthal multipoles, quadrupole and octopole that people argue about over coffee and never resolve. Coincidence? Maybe. But the chance alignment was enough to make people cautious and curious at the same time. Unknown to them across town, a separate group tried to break the effect by attacking selection. Uneven sky coverage can manufacture a dipole if you aren't careful. So they built mock catalogs with the same window function as the real observations, same telescope footprints, same redshift distribution, same signal to noise, and asked how often a fake dipole of the observed strength appears. Not never, not often, rare enough to keep the conversation alive. What nobody knew at the time was how messy instrument offsets could mimic direction. Spectrographs have personalities, a long-range distortion in one era, a CCD replacement in another, a slit illumination quirk that only shows up with certain seeing. So they cross-calibrated by anchoring segments to comb-stabilized spectra from different instruments. Some of the dipole amplitude shrank. It didn't vanish. When they weighted only the comb-anchored chunks, the vector drifted a few degrees but stayed upright. Meanwhile, in the clock world, a different kind of vector emerged. If a field couples to electromagnetism, each atomic transition has a sensitivity coefficient. Put those coefficients into a matrix, feed in the measured drifts, and the best fit direction is a set of couplings, not a point on the sky. The labs compared that abstract vector to the sky's spatial dipole by looking for a common phase. Did the months when the lab ratios peaked line up with the sky hemisphere where alpha looked higher? Within error bars, the answer leaned yes. Not a discovery, a rhyme. This was the moment everything changed in private meetings. Someone asked whether they should publish the vector, the sky coordinates of the fitted dipole, uncertainties and all. Publishing a direction invites a storm. If it's wrong, you become a cautionary tale. If it's right, you've just told the world that the universe has a faint arrow. The room split. Some argued for waiting on more web sightlines and more comb data. Others said the point of science is to share uncertain patterns and let them be tested. They compromised. A preprint presented the methods, the fits, and the caveats in thick paragraphs. The vector appeared small and shy, buried under stress tests, jackknifes, leave one spectrograph out, shuffle the dates, rotate the axis. A dipole persisted under most of them, not robust enough to claim a broken symmetry, too consistent to ignore. In the aftermath, critics did what they should, reanalyzed with alternate line lists, swapped priors on velocity component fits, and demanded that all wavelength solutions be published raw. Some signals softened. The dipole amplitude slid inside larger error bars, but the best calibrated cores kept hinting the same way. The pattern, if it exists, is faint. That's exactly what makes it interesting and dangerous. Because if there's a direction in the drift, the theories that fix the constants can't stay as they are. Fields would have to roll, and couplings would have to pick favorites. And that means the next chapter can't be about data alone. It has to ask which laws bend without breaking. Theories under strain, scalar fields and sliding laws. While data sketched a faint arrow, theory felt the floor tilt. The constants in our equations are really values set by the vacuum, numbers that fall out of fields settling into quiet. If those numbers drift, Something in the vacuum isn't sitting still. The simplest culprit is a scalar field, a quantity with a value at every point in space and time, rolling slowly down a potential, nudging the strengths of forces as it moves. Here, S where it gets concrete. Electromagnetism enters atomic transitions through alpha. If a scalar field phi couples to the electromagnetic sector, alpha becomes alpha phi. As phi rolls, alpha follows. Different atomic transitions have different sensitivity to alpha, so the pattern of clock drifts is a fingerprint of the coupling. The same trick works for the electron-to-proton mass ratio mu if phi couples to the Higgs sector or to light quark masses. Suddenly, the lab's ratio matrix is a window into the Lagrangian. This was the moment everything changed for the theorists in the room. A rolling field isn't just a tolerable tweak. It sits right next to an idea that's been haunting cosmology for 2 decades: dynamical dark energy. Quintessence, a scalar field whose slow roll provides the universe's late-time acceleration, has been considered elegant and frustrating. Elegant because it replaces a rigid cosmological constant with dynamics. Frustrating because it hides well. If the field that accelerates the cosmos also tugs alpha and mu by a trace amount, it finally leaves a handle. But there's a cost. Couple a light scalar to normal matter and you risk violating the equivalence principle, the promise that all bodies fall the same way in a gravitational field. That's not negotiable. Space missions and torsion balances have hammered those violations down to terrifyingly small limits. So models pull a trick called screening. In dense environments, the field's effective mass grows or its coupling weakens, muting its force. In empty space, it loosens up. Chameleons, symmetrons, dilatants, different recipes for the same Houdini act, evade the solar system, still breathe on cosmological scales. Meanwhile, something else was happening in string-inspired corners. The landscape of vacua comes with moduli, scalar fields describing the sizes and shapes of hidden dimensions. Stabilizing those moduli has been the core headache. If one's only almost pinned, it can drift slowly, shifting couplings by minuscule amounts. Runaway directions tempt you with dynamics and threaten you with fifth forces. Model builders drew boxes on whiteboards, allowed by clocks, forbidden by microscope, allowed by cosmology, forbidden by equivalence tests. The surviving space was small but not empty. Action moved to a working group that spoke both languages. They took the lab's sensitivity coefficients, how SR, IB, AL+, HG+ respond to alpha and mu, and fit them to simple phi models. Linear coupling, small potentials, a rolling rate tuned to today's expansion. The fit wasn't perfect, but it was coherent. The preferred coupling scale was high, the roll slow, the drift amplitude right where quasars and Oklo allowed. One parameter choice, the kind that makes people superstitious, predicted a subtle beat in the ratios with a period set by Earth's orbit and the field's shallow potential. If they were right, the next month would slightly sharpen the annual term in 2 independent labs. Get this, if the field couples to gravity's potential, the eclipse coming up would be a clean probe. Step the local potential with the moon's shadow, watch for a phase blip. That experiment got penciled in for later, but its logic shaped the theory. You could tell a smooth scalar roll from a step-like patch update by the profile of the signal. A field breathes, a patch jumps. Complications stacked quickly. Any non-zero coupling risks a composition-dependent force, so the models had to thread equivalence bounds at the part per trillion level. Laboratory tests of inverse square law deviations, lunar laser ranging, atom interferometers, all of them drew red lines. Theorists responded with screening parameters tuned tight enough to make engineers nervous. "You're balancing a coin on its edge," a metrologist said. "Yes," a theorist replied, "and the coin has a reason to stand." Parallel to the scalar story, alternatives tried to carry the weight. Varying speed of light ideas resurfaced, then mostly fell away. The data pointed to alpha and mu fingerprints, not a crude shift in C alone. VSL also fights hard against the scaffolding of relativity that GPS and particle physics rest on. Better to move couplings in step than to tilt the whole metric. The impact wasn't only philosophical. If alpha is alpha phi, the standard model's constants become addresses in a field space. The laws look less like commandments and more like a weather report, mostly stable, slight drift from a rolling pressure system. That reframes the job. We're not just discovering numbers, we're tracking fields. Precision metrology becomes cosmology at the bench. This was the moment everything changed in the narrative arc. Data had set the questions. Models handed back predictions with dates. One lab circled next month in red. Another drafted a protocol to blind the seasonal analysis. If the Scalar story lived through those tests, the vacuum wasn't a quiet stage anymore. It was an actor, moving softly, stubbornly, through our instruments and through the sky. If C slides, life, tech, and stars on edge. If the field is tugging alpha, people jump to a headline. Is the speed of light itself sliding? Strictly, alpha bundles E, H stroke, and C, and only dimensionless combinations carry meaning. But here's the practical truth engineers hear. Your conversions between time and length, frequency and energy, don't live on granite. Shift the underlying couplings and minute misfits creep into the joints of everything built on precision. Start small. A drift near 1018 per year sounds like nothing. It's not nothing to systems that integrate error. GPS lives by timing. Satellites broadcast clocks. Receivers solve for position by comparing arrival times to nanoseconds. With DriftAware relativity, it works. If clock species diverge in a way the model doesn't expect, satellite constellations start to disagree about distance by millimeters, then centimeters. One operator noticed weekly nudges in group delay that didn't fit solar weather. He logged them as solar noise and moved on, because there wasn't a checkbox for physics might be breathing. Semiconductors talk in frequencies. Phase-locked loops, laser links, coherent optical fiber, all depend on absolute stability in the oscillators that anchor them. A fractional slip at 1018 per year is a phase shift of a femtosecond per year on a gigahertz carrier. You'll never see it in a single device. You see it in networks when two independent chains don't drift together. Over 5 years, a doorstop of small corrections becomes policy. Data centers start exchanging metrology-grade timing, traces the way they once shared ping times. Chemistry is more forgiving than timing, but it has edges too. Fine structure splitting set details in atomic and molecular spectra, reaction pathways, and cooling lines in space. In the lab, a minuscule nudge in alpha won't change your beaker. In interstellar clouds, it tweaks the emissivity of the lines telescopes use to measure temperature and density. If those diagnostics shift, our inferred conditions shift. The danger isn't a broken reaction. It's a biased thermometer. Stars live at knife edges that look blunt because they're huge. Fusion rates in stellar cores depend on tunneling probabilities and screening, exponentially sensitive functions. A drift near 1018 per year across billions of years adds up. Run the model. Main sequence lifetimes could shift by fractions of a percent. That won't unmake the Milky Way. It moves the exact window for when a star like the Sun is most stable. Habitability budgets for planets adjust a hair. If the field's gradient has a direction, regions of the galaxy could experience slightly different histories at the limits of detectability. Here, where it gets human. An aerospace engineer in a cleanroom stared at a firmware constant he'd copied from a decade-old spec, the number that tied a frequency to a distance in a LiDAR altimeter. He'd always trusted it. Now the standards committee sent a memo with a sentence he'd never expected to read. Adopt ratio-anchored conversions where possible. He deleted the hard-coded number and rewrote the module to fetch a frequency ratio from a trusted timing feed. An invisible risk shrank by a hair nobody could sell in a press release. Complications keep honest people honest. Many systems self-correct. GPS has ground segments that nudge satellite clocks daily. Phaser measurement units recalibrate. Laser comms dither and lock. Those loops will swallow a slow drift if the models flex. The worry isn't immediate failure. It's pathology at the margins. rare events that cross thresholds because two loops were tuned with an assumption that no longer holds. That's how blackouts cascade, and how aircraft sensors disagree, just long enough to confuse a control law. Meanwhile, in astronomy, pulsar timing arrays aim for nanosecond precision across years. They already track Earth's motion and gravitational waves breathing. A scalar field drifting through alpha would add a weak, correlated term. If it's there, pulsars become spaceborne clocks that test the lab's claim from light years away. The crosscheck will sting if it disagrees. Meaning sneaks in where crisis usually lives. We design for certainty until certainty blinks, then resilience grows. DriftAware algorithms treat nature like a moving target, not a betrayal. The margin is where crises brew. We live in the margins and improve them. Not the first time either. The last alpha wars carved away false signals and taught humility. Back then, calibrators matured and some claims vanished. Some stayed. Beneath the loud debate, a quieter possibility kept gathering weight, maybe the constant's answer to their environment. If density and potential matter, seasons are a probe and eclipses are a gift. And that's exactly where the next fight heads. The Alpha Wars, data, doubt, and reputations. Before the whispers lined up, there was a brawl. People still call it the Alpha Wars, years when claims that Alpha had budged met a wall of skepticism, hard questions, and better tools. Careers bent around those arguments. Some never recovered. And yet, that fight taught everyone how to do this without fooling themselves. It started with good faith and rough rulers. Keck's HIRES and the VLT's UVES delivered exquisite quasar spectra, and the many-multiplet method promised sub-ppm sensitivity to alpha. Papers landed with dipole hints and ppm-level shifts. The reaction was instant. If true, it would scratch the cosmological principle and force new physics. But the measurements were perched on calibration ladders that nobody fully trusted yet. Here's where it gets concrete. HL spectrographs stitch orders together with THR lamps and polynomial fits. Over hundreds of nanometers, tiny long-range distortions bend the wavelength scale by tens of meters per second, enough to fake an alpha signal. HARPs, built to hunt exoplanets with ruthless stability, became a reference yardstick. Anchor UVES segments to HARPs, the distortions shrink. Add laser frequency combs and the ruler snaps straight. In the crossfire, claims were reweighed. Some evaporated under comb-calibrated re-reductions. Others softened but didn't vanish. A few carefully culled systems with clean velocity structure and independent crosschecks kept a faint, consistent sign. That was the lesson. The instruments weren't lying, but they were talking with an accent you had to learn. Meanwhile, something else was happening behind the scenes. Rival groups traded preprints and barbs, sure, but they also formed quiet alliances to test each other's pipelines. A team that had staked its name on a non-zero alpha shift invited a competitor to refit their spectra blind. Another group, famous for demolition, offered a comb run on the same quasar with a different instrument. You could feel a culture shift, fewer rhetorical flourishes, more raw files shared. A micro-story captures the mood. A postdoc who'd built their thesis on a dipole claim watched as a laser comb dataset sliced their sample in half. Half the signals died, the rest lived, smaller. They rewrote the conclusion with a knot in their stomach and sent the draft anyway. Months later, their caution was the reason a big lab called with a job offer. Reputation is currency, humility spends well. Calibrators matured. Supercalibration with solar twins and asteroid reflectance added crosschecks at the tens of ms level. Slit illumination tests, CCD stitching maps, and eidolon scans pinned down quirks people had waved away a decade earlier. The community learned the hard way that unresolved velocity structure and asymmetric lines can pull centroids. Higher resolution and more realistic component models cut those biases down. One notorious system, once a poster child, was retired after a telluric residual masqueraded as a shift. That hurt. It helped. Impact? The scatter narrowed. Large heterogeneous compilations gave way to curated gold samples where every assumption was challenged. When new near-IR spectrographs fed by adaptive optics joined the hunt, the game changed again. Different wavelength ranges, different systematics. A signal that survives across instruments, epochs, and methodologies gets harder to dismiss. But the scars stayed visible. Conferences remembered retractions like ghost stories, names spoken softly, caution lights flashing. Editors asked for comb calibration or a convincing surrogate. Referees demanded raw wavelength solutions, not just reduced stacks. The bar rose, and with it, the credibility of whatever squeezed over it. Meanwhile, the battlefield widened to include clocks. That altered the politics. You couldn't accuse a strontium lattice of sharing Keck's long-range distortion. You couldn't wave away a ratio drift by invoking slit illumination. Lab data brought a second, orthogonal axis of evidence. The fights got quieter, more technical, and, frankly, more interesting. The lesson that stuck was simple, stubborn, and earned. Instruments mature and claims survive only if reality backs them. The Alpha Wars weren't a detour, they were a filter. They taught everyone which errors hide where and how to keep them from becoming stories. They also taught restraint, publish vectors with caveats, predict beats you're willing to miss, and let rivals check your math. Underneath the bruises, something careful grew. A shared willingness to test the uncomfortable idea that alpha might not be identical everywhere and everyone. Not because it's exciting, but because the best calibrated data refused to cancel. And beneath the academic fight, a quieter possibility began to gather weight. Maybe the constants answer to their surroundings. If the environment matters, the next tests wouldn't require faith, just patience, seasons, and a clean eclipse. The hidden variable, environment-dependent constants. While the arguments cooled, a quieter idea kept returning. What if the constants aren't universal values but responses? Not noise, not error, environment, density, gravitational potential, even topology, conditions that could make a field stiff in some places and supple in others. If that's true, the question is, do they vary? It's where do they vary and by how much in our neighborhood? Start with the stakes. If constants respond to environment, then local tests can be exquisitely sensitive, not because the effect is huge, but because we live on a moving platform. Earth orbits the sun in an ellipse. Our gravitational potential changes predictably over the year. Tides swell and soften the local field. If a chameleon like Scalar couples to matter or potential, it hides in dense labs and peeks out in emptier stretches, leaving a seasonal fingerprint on clock ratios that no calendar should write. Here's what actually happened. Several labs already tracking slow drifts began to look for annual terms with fixed phase. They didn't fit arbitrary sinusoids. They locked the phase to perihelion and aphelion, the days when Earth is closest and farthest from the sun, and asked whether ratios gently nodded in step. In Boulder, hints from IB/SR. In Tokyo, whispers from Al+/IB. In Paris, a SR/HG plus pair that barely moved, just enough to keep the conversation alive. Each dataset alone was deniable. Together, their preferred phase lined up a little too well. Meanwhile, something else was happening in theory land. Chameleon fields, scalar fields whose effective mass grows with local density, were built for this. In dense regions, the field is heavy and short-ranged. In sparse regions, it lightens and reaches farther. That screening trick lets the field dodge solar system tests while still shaping cosmology. Symmetrons and dilatons add their own flavors of hiding, but the punchline is the same. Environment matters. A screened lab still feels a residue through unscreened apparatus, vacuum chambers, and the vacuum itself. The complication is brutal and familiar. Seasons also change temperatures, humidity, building vibrations, even laser room staffing. Thermal cycles can carry an annual period that looks like physics but isn't. So the metrology community did something patient. They lengthened the baselines. 3 years, 5 years. They moved transportable clocks between sites to see if a lab's personality dominated the signal. They stacked residuals across species with sensitivity coefficients baked in, so an environmental scalar would add coherently while mundane cycles would average out. The annual term weakened where it should and stubbornly sharpened where the coupling predicted. Not decisive, weighted preference. A microstory landed in a basement lab. An experimentalist who hated folklore started keeping a phase log, every maintenance event, every HVAC tweak, every time the cryoshield got nudged. He coded them into the analysis, then masked weeks around those changes. The annual wiggle lost a few false peaks. What remained pointed back at perihelion like a compass that had finally been demagnetized. Parallel to clocks, astrophysicists found a different lever: molecules. Certain molecular transitions, ammonia inversion, methanol torsion, are hypersensitive to the electron-to-proton mass ratio mu. If environment matters, dense star-forming clouds in diffuse regions might register slightly different mu, especially if a chameleon field threads differently through gas of varying density. Radio telescopes revisited well-studied clouds with upgraded backends. The result wasn't fireworks. It was a pattern of upper limits that tightened the leash, and in one carefully vetted sightline, a tantalizing non-zero at the edge of credibility. The teams called it what it was: a hint, doomed or destined to be eaten by a better baseline. While that was happening on the sky, Earth offered a lab-scale stress test: altitude. If a field couples to gravitational potential, moving a transportable optical clock from sea level to a mountain and back should imprint a tiny, predictable offset atop the normal relativity shift. 2 institutes ran the experiment blind. Different routes, different seasons, comb links humming. The extra offset, if present, sat right at the noise floor. The combined analysis leaned the same way as the annual fits. You could feel the room wanting a louder answer and accepting a quiet one instead. This was the moment everything changed in agenda-setting meetings. The proposal slate filled with environment probes, deep mine labs to push density higher, high-altitude balloons carrying portable ions into thinner air, fiber-link networks spanning north-south to flip the seasonal phase against local weather. Pulsar timing arrays added a coupling search to their pipeline, looking for a faint, yearly breathing tide to Earth's potential swing. A spaceborne molecular clock mission draft included an orbit designed to maximize modulation of any screened scalar. The impact was conceptual first, practical second. If constants respond to environment, then the universe isn't uniform in law, only in the rules that govern the rules. The cosmological principle remains mostly intact. On big scales, averaged laws behave, but locally you get texture. That texture gives you handles, seasonal clocks, altitude swaps, eclipses. It also gives you responsibility. You can no longer assume lab values travel unedited from basement to orbit to interstellar medium. What nobody knew at the time was how clean an eclipse would be. A sudden, well-modeled dip in gravitational potential sweeping across a continent is a sharp probe chameleons can't dodge without revealing their parameters. Teams started laying fiber and reserving gymnasiums. If environment mattered, the moon would write a signature in the ratios for everyone to read. Simulation or symmetry, the forbidden explanations. There's a question people whisper when data starts to bend intuition. What if the rules aren't drifting because of fields or symmetry? What if they're being edited? Not by nature, but by a layer above nature. The simulation idea shows up like a dare. If a hidden substrate runs our physics, constants might change the way a developer pushes an update. In patches, region by region, with seams that a careful observer could catch. Get this, if you really took patches seriously, the signature wouldn't look like a smooth scalar roll. It would look like steps, jumps, plateaus, maybe even different baselines tied to sky sectors if the renderer tiles the world. Discontinuities would betray grid lines. Temporal quantization could bleed into the finest clocks as jitter with a telltale spectrum. That's testable, not philosophically, empirically. Meanwhile, something else was happening in a corner office where physics met code. A programmer physicist who'd spent a decade shaving phase noise off lasers picked up the lab's drift residuals and overlaid them with server jitter from cloud backbones. The alignments weren't convincing, but the exercise sharpened a point. Clock noise carries a fingerprint. Real fields add correlated, low-frequency structure tied to gravitational potential and motion. Server noise adds artifacts anchored to maintenance schedules, diurnal load, and packet routing. The fingerprints differ. This was the moment everything changed in tone. People stopped rolling their eyes at simulation and started asking what the hypothesis actually predicts. If a patch system updates constants, you expect abrupt transitions and asynchronous rollouts. A scalar field, by contrast, gives you continuity, causality, and propagation speed limits. Eclipses become a discriminator. A clean, traveling potential dip should modulate a field smoothly across the network. A patch would look like a message, arriving with latency, not with the moon's shadow. Here's where it gets concrete. The Patch Tuesday crowd wrote down a toy, constant shift at intervals, pushed from a central scheduler with network lag and occasional retries. Feed that into a model of lab clocks and quasar sightlines. What comes out is ugly, piecewise shifts, site-dependent offset timings, no clean annual phase. The scalar model they were ignoring. It produced a sign on top of a slope, phase-locked to perihelion, with an eclipse signature that rose and fell like a low-pass filter tracing the shadow. Parallel to the drift profile, there's anisotropy. The spatial dipole in alpha, if it exists, looks like a gradient, not a mosaic. A gradient says symmetry broken once, gently. A mosaic says zones. People built sky tessellations and asked, do the best data cluster into tiles with distinct baselines? The result leaned away from tiling. Weighting by comb-anchored segments, the amplitude smoothed out. The direction persisted. That's more gradient than grid. The complication is philosophical seduction. The simulation story flatters the storyteller. It offers agency and narrative in a place we're trained to strip those out. The danger isn't that it's false, it's that it invites lazy fits. So the bar went higher. A lab would not accept a patch claim unless someone predicted a maintenance Windows echo in ratios, with phase and amplitude nailed. No one could. The Scalar team, by contrast, put dates on their wobble and amplitudes on the eclipse. A human moment kept the room honest. At a seminar, a young researcher pitched a clever test. Look for pixelation in ultra-high-energy cosmic rays, direction-dependent cutoffs that would betray a discrete lattice. A senior cosmologist nodded and said, "Great test. Wrong scale. Our alpha drift is whispering at 1018 per year. If there's a lattice, either it's hidden far below or it's not talking to this." The student did fold. They refined the proposal to hunt for step-like features in long baseline timing data during known network outages. It was disciplined. It came back null. That mattered. Meanwhile, in the astrophysics stacks, CMB anomalies sat like a Rorschach test. Low-L alignments, a hemispherical power asymmetry, oddities that tempt big stories. The dipole in the matter distribution looks too large, pointing near the CMB dipole. Does that argue for a cosmic preferred direction or for local structure contamination? The drift narrative slots into the first column. A faint, global gradient seeded early, preserved across epochs. The simulation patch idea has to juggle too many coincidences. Why would update domains align with cosmic structures we didn't lay out? This was the moment everything changed for people on both sides of the metaphors. The lab teams agreed to a clean shootout, used the upcoming eclipse as a falsifier. The patch model predicted either nothing or a jagged, asynchronous blip uncorrelated with the shadow's motion. The field model predicted a smooth, low-amplitude phase blip with a known sign and time profile. They wrote both predictions down, time-stamped them, and posted them where critics could see. Impact isn't only about what wins, it's about how you lose. If the eclipse produced nothing, the scalar fit would tighten or die. If it produced steps, the simulation idea would earn a seat at the adult table. Either way, a disciplined test would keep the story from drifting into vibes. What nobody knew at the time was how much coordination the eclipse would force: fiber links, cross-continental ratios, raw logs posted live. That pressure would make metrology act like an observatory. One more reason to keep symmetry in the frame: fields care about conservation laws, patches don't. A sliding law with a Lagrangian respects energy bookkeeping and causal light cones. A patch can sidestep both unless you smuggle in a metaphysics that looks suspiciously like a field. That irony wasn't lost on the room. So yes, the forbidden explanations got their day. They gave us sharper tests, cleaner predictions, and a reason to wire the continent like a single instrument. And as the moon's shadow approached, labs weren't debating worldviews anymore. They were watching for a phase line to move, or not, on screens that had learned to hear the universe breathe. The Metrology Summit, when the world recalibrates. While theories argued and eclipse plans took shape, a quieter crisis hit the people who keep the world on time. The BIPM NIST PTB, the alphabet of metrology, started getting calls from industries that never call. Grid operators, satellite constellations, banks. The question was simple and terrifying: if constants drift, what happens to the second? The room in Severs felt like a control center disguised as a conference. Coffee, nameplates, fiber maps on the wall. These were not physicists chasing wonder. They were custodians. Their job was to keep definitions boring. Now the proposal on the table did the opposite. Stop pretending the second is a single number realized by a single species. Start treating it as a living average of ratios. Action first. They put up the backbone. More than 400 clocks in 60 countries already feed International Atomic Time. Each gets a weight. A weighted average becomes the heartbeat the world follows. But those clocks skew microwave cesium, the current definition. Optical clocks, SR, IB, AL+, HG+, beat with far higher stability, already contributing as secondary representations. The plan was to flip the posture. Elevate cross-species ratios to first-class citizens, use them to watch for drifts, and distribute time with DriftAware metadata attached. A technician from a national lab told a micro-story that cut the theory talk short. He detaped a note above a rack: trust ratios, not absolutes, and it changed how his team debugged outages. If we stamp every packet with which ratios we used and when, he said, we can unwind anything that goes wrong. The room went quiet, not from romance, but because that sounded like resilience. Complications stacked in predictable piles. Industry doesn't like moving targets. A satellite operator asked who would be liable if a DriftAware firmware update bricked older receivers. A financial compliance officer asked how to audit trades if the time source is a vector, not a scalar. A legal team wanted to know if a provisional second could stand up in court. The metrologists met those questions with drafts. A provisional standard with versioning, cryptographic signatures on time packets, and a guarantee that the new feed would degrade gracefully to legacy behavior if a client ignored the extras. Meanwhile, something else was happening in the standards subcommittees. The planned redefinition of the second, optical, by 203 if all boxes were checked, suddenly had a new column: drift monitoring. They wrote criteria in that cautious language only standards bodies love. Sustained intercomparisons across at least 3 national metrology institutes, agreement at uncertainties equivalent to losing less than a second in billions of years, and demonstrated ability to detect a fractional drift at 1018 per year across multiple species. It wasn't flashy. It was a gate. They had to touch the meter too. Length is defined through C and the second. If you treat the second as ratio-anchored and drift-aware, the meter inherits the metadata. Engineers grimaced, then nodded. If the packets carry the context, lasers can lock to ratios and length stays sane. The impact of adopting even a provisional protocol was immediate. Time transfer links, fiber and satellite, started embedding correction fields that could carry a cosmology term, set to 0 by default. National labs published public dashboards. live ratios, uncertainties, residuals after environmental corrections. A quiet revolution in transparency followed. The people who had once guarded raw logs like crown jewels posted them with explanations a graduate student could follow. It wasn't all harmony. A consortium of manufacturers pushed back, arguing that compliance costs would hammer small players. The summit answered with a staged rollout. Advisory now, mandatory later if the Eclipse and subsequent tests stayed consistent. They also funded a reference implementation, open software that any vendor could drop in to parse DriftAware time. Liability moved from suspicion to shared tooling. A moment crystallized the shift. A senior metrologist who had spent 20 years defending cesium's honor said, "We're not replacing the second today. We're acknowledging that the realization of the second breathes through more than one atom. We'll watch it breathe together." It read bland in the minutes. In the room, it felt like a hinge turning. Outcome: a provisional standard, historic in its caution. Time packets gained fields for ratio provenance, environmental context, optional drift terms. The second stayed defined by cesium, but the world began to steer by an ensemble that admitted motion. The standard was explicitly reversible. If replication failed, the cosmology term would sunset. If evidence grew, it would graduate. While that was happening on paper, cables were being laid. A ring of optical links was planned across the path of the coming eclipse, labs volunteering gymnasiums and rooftops to house transportable clocks. The summit's bet wasn't that constants drift. The bet was that if they do, we can hear it, compare notes in real time, and keep planes landing, trades stamping, and grids humming while the laws breathe in the background. The eclipse test, a day the clocks held their breath. The week of the eclipse felt like wiring a continent to listen for a sign. Transportable optical clocks rolled into gymnasiums and observatory foyers along the path of totality. Fiber spools fed combs. GPS-disciplined links handled redundancy. Labs that normally guarded their timing like state secrets opened ports and posted live dashboards. The plan was simple in outline, brutal in detail. Watch the gravitational potential dip as the moon's shadow swept by and see if the ratios blinked in a way only a field could explain. Stakes were written on whiteboards in 3 columns. First, the clean prediction, a smooth, low-amplitude phase blip, sign fixed by the coupling rising and falling with the shadow's motion. Second, the null, nothing beyond standard relativity's gravitational redshift already modeled. Third, the jagged alternative, steps, lags, or site-specific hiccups, the patch signature. If the eclipse produced nothing, the scalar fit would tighten or die. If it produced steps, the patch story would earn a seat at the table. Either way, the point was to let the clocks decide. Action started hours before first contact. In Oregon, a strontium lattice clock, transportable but temperamental, locked to its cavity after a stubborn hour of thermal settling. In Texas, an aluminum-ion clock shared its frequency via comb to a local ytterbium lattice, the ratio streaming in millihertz ticks. On the East Coast, a mercury-ion standard stayed off the path but served as a control, feeding a steady reference into the network. Each site tagged packets with temperature, magnetic fields, local accelerometer noise, and a flag for any human touch. While that was happening in gymnasiums, fiber operators traced routes like chess moves. Redundant paths looped around construction sites. A microwave link rode a rooftop line-of site where fiber couldn't reach. The summit's provisional protocol stamped every dataset with provenance. Which ratios, which couplings, which environmental corrections. It read bureaucratic. It was the backbone of trust. The first shadow hit and nothing obvious happened, which was exactly what should happen if the effect lived at the level people expected. On screens, residuals after the standard gravitational redshift correction looked like flat lines with nervous scatter. Then, as the shadow moved, a tiny bow began to form in 3 independent plots. IB/SR in Salem, AL+/IB in Dallas, SR/HG+ in Cleveland's Penumbra. The bow was a few parts in 1018 high at peak, broad like the shadow's footprint, not a spike. A student in a gym-turned lab leaned into a microphone she didn't need and whispered, "It's there." She'd rehearsed not to say it. The habit broke anyway. Her advisor raised a hand and pinched the air, a signal to breathe. They let the data fill the room. Complications arrived on schedule. A cloud bank in the Midwest cooled a roof unit and nudged a cavity's temperature control into a tiny oscillation. The control flagged itself. The site's ratio plot showed a ripple that was out of phase with the shadow. The pipeline downweighted those minutes. Meanwhile, a small earthquake off the coast barely kissed a West Coast lab seismometer. The active isolation swallowed it. The plot didn't care. Impact landed not as fireworks but as convergence. When the path had crossed the Atlantic and the last totality ended, the teams froze the streams and ran the fit. They subtracted modeled redshifts, folded the ratios against the shadow's ephemeris, and stacked species by their sensitivity coefficients. The composite trace looked like a breathing line. The amplitude matched the low end of the scalar prediction within error bars. The phase was right. The patch team's step templates failed to grip. Cross-correlation preferred smooth. Skeptics did what they promised. They asked for raw logs, everything, not just the curated streams. The organizers posted them within the hour, file names unromantic, checksums public. An independent group in another time zone built their own analysis from scratch and got the same bow, slightly smaller. They found a typo in a metadata tag at one site and posted a fix before anyone could tweet a conspiracy. The tone stayed adult. A micro-story capped the day. In a control room far from totality, a veteran timekeeper who'd spent decades watching numbers not move reached for a Sharpie he kept for boring nights. He drew a dot on his notebook at the time the composite peaked. Then he wrote 4 words he'd never expected to write. Cosmology term went live. Meaning didn't arrive as a verdict. No single day can certify a drift in the rules. The Eclipse test wasn't decisive alone, and everyone said so out loud. But its weight shifted the center of gravity. The summit's bet that a DriftAware network could catch a clean, correlated signature looked wise. The null hypothesis survived in spirit. The bar stayed high. But the field hypothesis earned a stripe. A timely, sign-fixed, multi-site blip that standard models couldn't fully explain, with amplitude and phase consistent, within uncertainties, with a smooth scalar response to a changing gravitational potential. This was the moment everything changed in how the community moved. Replication schedules were drawn while the coffee was still warm. A second eclipse path overseas became a priority. Portable clocks that had been science demos were booked like headliners. Pulsar timing groups slotted the eclipse's time window into their own residual searches, just in case the field breathed through their baselines too. What nobody knew at the time was how much the quiet parts would matter. The open logs, the provenance stamps, the grace with which a lab admitted a heater glitch. Those choices turned a risky spectacle into a disciplined measurement. The day the clocks held their breath, they didn't gasp. They exhaled together just enough for us to hear. Crisis and continuity, systems under the new rules. The morning after the eclipse, engineers woke to inboxes full of cautious verbs. Prefer, provisionally apply, monitor, rollback plan attached. DriftAware time had moved from whiteboards into firmware. Aviation first. Flight management systems depend on blended navigation. GPS, inertial, radio beacons, stitched by timing. Airlines pushed an overnight update that let avionics read the new provenance fields in time packets. If the cosmology term flickered, guidance would wait inertial more until the network settled. Pilots never saw a message. The best changes make quiet flights quieter. On trading floors, compliance officers did something they'd avoided for years. They called the Metrology lab by name in a policy memo. Timestamps on orders now carried a hash of the ratio set used that day. If auditors rewound a disputed millisecond, they could reconstruct which clocks, which corrections, which DriftAware factors shaped it. A risk buried in legalese became a line item with a checksum. It felt like overkill until it didn't. Power grids live or die by phase. Operators rolled out an update to phaser measurement units that could ingest the optional drift field. The first week looked boring by design. Then a heat wave hit, and a transmission corridor ran hot. Line trips cascade when protective relays disagree by a whisker. This time, a substation's local oscillator had started to wander while a neighboring unit held steady. The network's DriftAware waiting downshifted trust in the sloppy node for 2 minutes. Operators rebalanced load. A blackout that would have been a case study became a footnote titled "Boring Correction Applied." Nobody cut a ribbon for it. They archived the incident with a sigh that sounded a lot like relief. A microstory unfolded in a fluorescent-lit lab stacked with legacy boxes. An engineer stared at 6 characters in a header, C-fixed, hard-coded into firmware a decade ago to tie a frequency to a distance for a factory robot's LiDAR. He defended that line through 3 audits. Now the vendor shipped an update that replaced it with a call to a ratio service, signed by the national lab, cached locally with fallbacks. He hovered over the keyboard, deleted C-fixed, and watched a test arm trace the same arc it always had. Nothing changed. Everything changed. Meanwhile, satellite constellations started cross-checking against each other, not just their own ground segments. Galileo, GPS, Beidou, QZSS, ordinarily polite rivals, agreed to share DriftAware deltas under the summit's protocol. Receivers that could read the extra fields began treating time like an ensemble. Those that couldn't continued blissfully. The sky did not fall. It learned to hum in tune. Complications tried to sneak in under friendly names. Autocorrect, loops that were tuned against a world with no cosmology term, began to amplify a seasonal edge case in one vendor's receivers. The fix was simple: widen the loop's time constant by a hair, and teach it to ignore the provenance it didn't understand instead of misreading it. A week later, an advisory landed in inboxes with a sentence that would have been science fiction last year. If the cosmology field is present and unauthenticated, ignore. If authenticated, wait by declared uncertainty. Across the Atlantic, maritime navigation crews ran a drill. What happens if the new fields go dark? Ships fell back to inertial and celestial routines, then rejoined the network without fuss. Redundancy stopped being a checkbox and became a choreography. Science instruments adapted too. Radio observatories folded DriftAware time into correlators and logged the cosmology term alongside weather. When a millimeter array stacked baselines over a month, the residual phase smear shrank by a measurable, mundane amount. No headline, just cleaner images of a dusty disk where planets learned to be. Policy followed practice. Regulators published a light-touch rule. Time sources used for safety-critical systems must declare ratio provenance and support a rollback to legacy behavior. No fines yet. A clock, after all, had just convinced the world to change paperwork before changing definitions. Meaning crept in through routine. Teams wrote runbooks with a new section, Cosmology Anomalies, and then left it mostly blank because the note was enough. Resilience grew because certainty had shrunk in public. People who once sold precision as permanence started selling it as continuity, a promise to keep pace with a universe that breathes. And when the inevitable glitch arrived, a transportable clock in a mountain lab lost lock during a storm, the network didn't panic. It flagged, rerouted weight, and filed a report with raw logs attached. The report's last line read, "No customer impact." In that margin between fear and function, humility became policy, and the world kept time without pretending time was a statue. What the universe admits, a moving target. By the time the Eclipse plots cooled, the question had shifted. We weren't hunting a loophole anymore. We were watching a living number trace its path through our best instruments. The identity of science was on the line. Are we discovering fixed laws or tracking fields that happen to be quiet most of the time? Here's what the universe admitted carefully, through convergent evidence rather than a recap. The sky offered hints of a gradient, quasar sightlines leaning one way, then the other, faint but structured when calibration improved. The Earth's deep memory tightened the corridor, Oklo's fossil reactor telling us that, averaged over eons, any drift had to thread a narrow pass. The lab, relentless and domestic, turned ratios into a daily chronicle, optical clocks agreeing to disagree by parts in 1018, seasonal terms peeking in with the right phase, and a clean eclipse bow that rose and fell with the moon's shadow. None of these could stand alone. Together, they started to rhyme. The meaning wasn't that laws broke. It was that laws might be values of fields and fields move. In textbooks, constants look like carved numbers. In practice, they're addresses in a landscape, vacuum expectation values that can slide on slopes so shallow we'd miss them for a lifetime, unless we put the right rulers in the right places. Precision became a frontier of wonder, not because it gave us more digits, but because it let us feel a pressure system in the vacuum. Meanwhile, something else was happening in the human arc. The grad student from the cold open, the one who paused before logging the first anomaly, found themselves running a lab that didn't treat drift as a rumor. Their group posted raw logs as policy. They built a wall of clocks with different sensitivities on purpose, then listened for the chord rather than a single note. On a quiet afternoon, they taught a first-year student how to read a ratio matrix like a weather map. High pressure here, low there. A front crossing next month if the model's right. The stakes rippled outward, past metrology into the way we talk to the sky. Pulsar timing arrays added a scalar coupling template to their search for nanohertz gravitational waves. A molecular clock in low Earth orbit, built to test mu with methanol and ammonia, filed its launch window. A DeepMind lab installed a transportable ion trap 4 kilometers down to push the coupling to density. Space agencies compared orbits to maximize environmental modulation. These weren't stunts. They were the normalization of a moving target. We learned restraint the hard way. Theories promised beats with dates, and when a forecast missed by a hair, the team posted the miss in the same breath as the data. Critics refit with new priors and found the amplitude a notch lower, the phase a hair later, still coherent within error bars. Confidence didn't sprint, it walked with a hand on the rail. That pace was the point. The broader meaning landed where good stories do, in the way we behave. Engineering accepted humility as a design principle. Standards bodies learned to annotate reality instead of pinning it down. Astronomers added a line to figure captions. Assumes DriftAware calibration. Physicists stopped insisting that variation affronts reason. They treated it as information about the vacuum we happen to inhabit. Yet this curiosity came back sharpened. Once the fear subsided, people started asking better questions. If there's a spatial gradient, what seeded it? Inflationary relic? A nearly pinned modulus? If a field rolls, what anchors its potential? Can we catch a correlation between dark energy proxies and clock drifts? Is there a symmetry that keeps the equivalence principle safe while letting alpha breathe? The map of open problems grew interesting edges we could actually walk toward. And then there was the quiet grace of continuity. We kept planes landing and grids balanced while acknowledging motion underfoot. The world didn't need a new constant chiseled in stone. It needed a way to talk about change without breaking trust. That's what the Metrology Summit gave us. A language for a living second, a meter that inherits context, a packet that carries provenance. You could feel the field's presence without treating it like a crisis. The grad student, now a pi, stood in front of a whiteboard with a list of nexts, pulsar crosschecks, a polar orbit to flip seasonal phase against Earth's weather, a joint run with an atom interferometer to probe chameleon screening. They paused, capped the marker, and said what everyone in the room already felt. We're not chasing a glitch, we're tracing a contour. A contour means there's terrain. It means the laws we write are topographic lines, locally straight, globally curved. It means science keeps its promise not by pretending the world is static, but by measuring motion with enough honesty that meaning survives the drift. Resolution and meaning. The rules didn't shatter, they breathed, and we learned to measure the breath without losing our step. If you want to see where this contour could lead, spaceborne clocks, pulsars, and the next clean test, subscribe and cue up our deep dive on the cosmic glitch that started it. It links the first whisper to the eclipse bow you just saw.